Alright, so in the third part of this class, I will describe a few of neuropsychology's imaging methods. But first, let's start by exploring how neurons work at the chemical level. Because the neuron is the Lego block that forms our experience of the world. Just like Müller discovered 2 centuries ago, the sensorial receptors are a type of neuron with a specialized structure that permits it to react with a higher sensitivity to a specific type of energy corresponding to a sense. It's important to note that neurons are little tubes containing aqueous liquid with charged atoms or ions, and that they are themselves also swimming in a charged aqueous liquid. When resting, the neuron has a lower charge than the liquid it's in by about 70 millivolts, mainly because it contains less sodium, which has a positive charge. If this is the receptive neuron in the skin of your finger, putting pressure on it will effectively bring in some sodium. This process would make it gradually depolarize, meaning that its charge would become more and more similar to its surroundings by going up. Minus 65, minus 60. If the neuron reaches minus 55 millivolts, though, it just loses it. What I mean by that is that next thing you know, all the freaking sodium is in the neuron, like it's having a bad breakup in the middle of a grapefruit diet. Seriously though, before he reaches minus 55 millivolts, you might be able to talk him out of it and the chemistry will restore its balance. But minus 55 millivolts is that threshold after which it's just too late to even bother. As the neuron is spreading its Vegemite on its lined up cheeseburgers, there's an electric impulse called action potential that flows through its body to forward the news to the next neuron. He left me. Or just ouch. During that time, the sodium goes all the way up to plus 40 millivolts, as you can see on this graph, until the guilt of the sodium binging is just too much, and you must let chemistry deal with restoring itself once more. That initial creation of an electric impulse in response to a physical stimulation is called transduction. From their dendrites, which is where they receive signals, to their axon, where they release their own, neurons can measure as much as a meter in the leg, or be as short as a few microns in the brain. They don't touch each other though, because they're kind of awkward with handshakes, but they're only separated by a microscopic space. This small space between each of them is called the synaptic cleft. And since the signals only go in one direction, we can call the previous neuron presynaptic and the following, you guessed it, postsynaptic. Postsynaptic, yes, good job. When our first neuron has transduced the physical signal into an electric impulse, it wouldn't be rude to just send that raw electric discharge to the next neuron. And so, what actually travels in the synaptic cleft are those little keys called neurotransmitters. I call them keys because they each have a specific shape that may or may not be compatible with the dendrites of the postsynaptic neuron. When they are compatible, some of those keys depolarize the postsynaptic neuron, like we've seen, while others hyperpolarize or increase its negative charge. What does that do? Well, that would effectively inhibit its chance of reaching the minus 55 millivolts threshold, and therefore of propagating the action potential. Now, just like I actually, neurons love to rest. And so every time they pass the action potential forward, they promptly return to their minus 70 resting state until they are receptive to be depolarized again. You all follow me so far? It's not too complicated. Now, you might be actually quite surprised by how simple it all is when you consider the complexity of experiences that neurons can make you feel only by creating action potentials and passing along neurotransmitters. Because neurons cannot fire two action potentials at once, or even just fire a bigger one for that matter. Their only dilemma is simply to fire or not to fire an action potential. Well, if that's the case, how can intensities of stimulation be transmitted to the brain, you ask? Think about it. I mean, if your actions are strictly binary, if you could either bark or not bark, how would you express a particularly important enthusiasm? I mean, if you can't bark louder, then all you can do is to bark many times and quickly, basically to suddenly increase the frequency of your barking. That's exactly what neurons do. Well, they don't exactly bark, but the point was that they take the shortest rest between each action potential, just enough to restore their chemistry in order to increase their firing rate. Those short rests are called refractory periods. And in practice, they will limit the neuron's maximal frequency at around 100 impulses per second. They might not sleep as much as I do in the end. Fun fact, did you know that your electronics, even when they are turned off, continue to consume some electricity? That's right, and that's why it can be wise to unplug your appliances before you leave for an extended vacation, except maybe for your refrigerator. You might want to leave that one plugged in. Your neurons function in the same manner. Even when they are not being stimulated to reach minus 55 millivolts, they still exhibit a spontaneous activity of low frequency that does not lead to any sensation. Researchers are able to inhibit the spontaneous activity of neurons for a short moment, but that always leads to a brief surge of activity afterwards, like to compensate. In the same way, a prolonged excitation will momentarily lower the spontaneous activity of neurons. So, to sum up, you have a physical stimulation that is captured by a receptive neuron. Once that neuron receives sufficient activation, it transduces that stimulation into an electric signal and sends the first action potential to the postsynaptic neuron via neurotransmitters. If those neurotransmitters are excitatory and succeed in depolarizing the next neuron until minus 55 millivolts, that next neuron will forward the action potential. If that action potential reaches the brain, then you can have your beautiful perceptual experience. As I've mentioned, neurons have binary responses of either firing or not firing. And so they signal intensities of stimulation via their firing rate. Spoiler alert for next lecture, however, in some cases, such as in the transduction of light, the amount of photons, so the intensity of the light, is not signaled by a frequency, but rather by a response strength. So that's different. We'll explore this confusion at a later date, but for now, let's take a short rest to restore chemistry, shall we?